to identify this relationship. Model the outcome as a function of the treatment. These mediators, and again, relevant covariates, use an appropriate regression model at each step. You get your regression estimates, and then you use Monte Carlo simulation to take draws from the outcome values predicted by each of these regression models, and you plug those in sequentially. So what that means is you do your regression model, let's say for M1, and then you say, well, holding A at some level, let us estimate the distribution of the M1s. And we can take a draw from the distribution because the regression model is going to have an error term. Then let's hold A at some other level and take another set of predictions of M1 when A is held at A star. And you can do this for each of the M's. You can also do this for the Z. And then you're going to plug those values into the regression for Y to be able to get at each of these expectation terms. So you're going to hold A at the level you want, you're going to hold the M's at the level you want, and the Z at the level you want. And when we're talking about M's and Z's, we are using the draws which we came up with in the previous step. Using those, get one draw for the distribution of outcomes, therefore corresponding to A at some level and M's at some other level. Repeat this procedure many times, and each time you take the average of the Y. And so the average of the averages across these Monte Carlo draws gives you the counterfactual which you want, corresponding to each of these E terms. So you do this for each of the E terms, then you simply take the difference, and that gives you what you want. And you calculate standard errors by bootstrapping. So as you can see, there's a lot of simulation required, and bootstrapping increases that computational burden. So it's sort of an inefficient, computer-wise inefficient way of doing it. Nevertheless, it gives you the estimates which we require. And this paper, Daniel et al. Sort of puts that in very clear language and suggests how to go about implementing it.
Are the M's drawn independently from each other?
So that depends really on the model. You have to, so for example, if the model for M2 includes M1, that is to say, if you think M1 causally affects M2, then M1 will be part of that model. But if they are all independent, then yes, they will be independent. But you need to therefore map out what are the different causal influences. And if M1 impacts M2, which also impacts M3, then the model for M3 must contain M1 as well as M2. Okay. That is sort of a decision you need to make as based on contextual information of the field. And in that sense, the model is something very much which you are going to define, and therefore whether some terms are independent of each other is a decision you need to take as the modeler.
I see. Okay.
Sunil, I just got a little confused. So the relationship between M and Y is kind of so that doesn't depend on the treatment, right? So essentially, how a particular attribute of a person
correct yes.
on the output, that is held to be stable. And
correct.
So the only differences come from the different distributions of M across the two treatments.
Correct. Yes. However, that is in the case of statistical discrimination.
Yeah. I meant
yeah.
that. Yeah.
Yes, very much. Yeah. Okay, so here is our implementation. We are using 3 years of data from the NYPD, which is easily downloadable. This is a popular data set and has been used by many authors. These are a few recent papers. The main aim in this literature is to rule out sources of statistical discrimination and therefore isolate or prove the existence of race discrimination. So the major difference between those attempts and ours is we are instead trying to estimate both of them simultaneously. If we have more time later, I'll come back to this paper by Knox et al., who also use the idea of a mediator, and they are using the decision to stop as a mediator. The idea being that if you want to look at racial discrimination, of course, you want to look at the treatment of those people who have been stopped, but to generalize it to the population, you also need to know something about the people who were not stopped. So in order to get at that distribution, they specify the decision to stop itself as a mediator. And so they use some of the machinery around causal mediation to sort of attack a different dimension of this problem. But I'm happy to come back to that later in the Q&A.
Just a quick question. So I'm just wondering, how is your setup any different from the causal mediation models in the psychology or psychiatry literature? Like initially, I was thinking that the role of the unobserved, confounders were somehow being explicitly modeled, but perhaps that's not being the case. So how is it, any different from that literature in the psychology where it's essentially known as the causal mediation models, right?
So it is not different. It's very much an attempt to say discrimination is best treated as a problem of causal mediation. Now, we will make some progress when in a few slides in saying if you cannot observe beliefs, or if they are inaccurate, or if they are biased, or if they are prejudiced, what can we then do? So we are going to use some machinery for treating an unobservables problem to address that problem. But in terms of the definition, it is squarely a definition in terms of the causal mediation literature, as you mentioned, epidemiology and psychology and political science.
Okay, thanks.
So here is our first attempt, an extremely simple causal model, which is simply saying, look, there is race. There is the suspicion about which type of crime this person has committed. And there is the possibility, indeed empirically seems to be happening, that suspicion varies according to race. And that this suspicion then goes on to determine the outcome. Now, to be very clear, we are focusing on the outcome of a search or frisk. So we are looking at the population of those who have been stopped, and we are considering 0-1 outcomes in terms of were they then subjected to a search or frisk, yes or no. So our discrimination estimate is very much going to be around the treatment post-stop, as different from, in some of the literature, whether the decision to stop itself reflects discrimination. So that's something important to specify. So here is our, as I said, very simple graph. And now we've implemented the algorithm, which I spoke of 2 slides back, which is we are estimating suspected crime using a multinomial logit. And we're modeling search or frisk using a logit. And we are, in the simplest case, using no covariates at all to get these estimates of statistical and taste discrimination. And then progressively, we are adding more and more balancing covariates, by which I mean in order to identify those different relationships between race and suspected crime. So we would like to control for precinct, definitely, or for physical characteristics or the date and time. And likewise, the causal relation between suspected crime and the search or frisk outcome, and then between race and the search or frisk outcome. So all 3 sets of these, all 3 causal relationships, to identify these, we are progressively adding these covariates, which indeed are standard and have been used in the literature. So what we see is that, so first to specify, our results are in terms of odds ratios, the odds of a stop, the odds of a search or frisk for the population of those who have been stopped. So with no covariates, you have roughly 20% higher odds for a Black person, 20% higher odds being explained as statistical discrimination, and 42% higher odds being explained as taste discrimination. Compare both these figures with the observed odds, which is 1.68, so roughly 70% higher. So neither taste nor statistical is going to fully account for what's happening. So there is obviously a lot of variation being explained by these other covariates, precinct, physical characteristics, and so on. Nevertheless, these are the sort of estimates corresponding to this causal model for statistical and taste discrimination. And both of these start falling once you add in more and more covariates. So much so that statistical discrimination, something's happened on my, screen. I need to annotate again, Yeah, so much so that statistical discrimination is effectively 0. So the odds are roughly still 1, but taste discrimination remains about 25% results in an odds roughly 25% higher once you've controlled for all these other covariates. And then if we break this down by the stop reason, then you can see, well, there are certain patterns which sort of map onto what our intuition would tell us, that like the scope for subjective judgment is highest in self-initiated stops. And indeed, the taste discrimination in those ones tends to be the highest. And it sort of is lower for the other cases. For casework, it's seen there is still some taste discrimination, but it's a lot lower. It's only 15%. Are there any questions on this?
Just wanted to clarify, you mentioned that this is based on a sample of those observations where people were stopped, so conditional on being stopped. But the decision to be stopped itself is one where discrimination could take place?
Very much. I completely agree with you. And sort of we've deliberately, that problem is called the problem of missing zeros, that we don't observe the people who've not been stopped. We are deliberately trying to avoid that problem because our aim really in this paper is to say, with this machinery, what is the best you can do to estimate discrimination? Now it's a separate problem. How can I extrapolate from that to the population overall and not just the sample, which we're looking at, the sample of those who have been stopped? So by no means are we claiming that these figures extrapolate to the full population of people walking on the streets. We are saying this is very much the estimate for those who have already been stopped. In theory, it would get a lot more complex in terms of computation, but what we could do is use the method proposed by these guys, Knox et al. Sorry about the annotation. Yeah, these guys provide this idea of saying, look, consider the decision to stop itself as a mediator. So then we'd have to have sort of a two-step process. One mediator, whether you're stopped. Second mediator, suspicions. And we'd have to specify, well, at what point do suspicions affect the decision to stop and the decision to search and frisk, or is it a stepwise sort of procedure? So this would require a lot more model heavy assumptions to be imposed. And so at this moment, we are avoiding that when we're sticking to a simpler problem. So hence, yes, is the short answer to your question, and this was the longer answer.
Sorry.
Yeah, Sunil, can you just explain those results? What do you mean by casework and radio run?
Okay, sure. So basically, the data tells you a couple of things. Of course, it tells you the race of the person who stopped, the reason why they are stopped, which is coded as these suspicions, which is sort of our operative main variable for defining statistical discrimination. Then it also says circumstances of the stop, and that is this 3-valued variable, which has these 3 options: a self-initiated stop, or as a result of ongoing casework at a scene, or because you received a call on the radio as a result of which you ended up stopping somebody. So that's sort of distinct subsamples within the overall data. So that's why if you add these numbers up, they should come to the overall, the full sample number of roughly 33,000. The reason for breaking up clearly is, well, you could think of different motivations and therefore different extents to which discrimination may or may not take place, depending on these circumstances.
Right. Okay.
Yeah. Should I go on?
Yes, go ahead. I think topic question.
Yeah. So do you have information on subsequent, post stop or frisk, whatever it is? Do you have information on whether an arrest was made, whether the person was incarcerated? Because that can, so conditional on being stopped, so for example, you're stopped and it's a random stop. Okay, you suspect something that been going on, you stop the person, and then of course at that point you can have more information from your license records if you have any prior arrests, any prior incarceration. on that, you can take a call about whether to escalate the case or let the person go based on their prior records, right? So that will perhaps be some more objective way, because in that case, perhaps the case discrimination would not play as much of a role in that case. Because if you, for example, if you just look at the case of two random people, okay, being stopped, but for the same reason, for example, okay, same black teenager, similar ages, but then one has a prior record of being arrested, but the other does not. Based on that fact, your subsequent action will be based on whether you have that prior record or not, right? So that will deal perhaps be more of, I mean, less of case discrimination compared to, you know, if you did not have that information.
Yeah,
so
I completely agree with you. That would help. We do observe post-stop events. So in the paper, we have sort of an additional version of this where we look at a 3-valued outcome, where you searched or frisked, or were you directly arrested. But what we don't observe is the thing you said towards the end, which is whether you have a prior arrest record. So we don't know what took place and what information was exchanged in the process of the stop. We can only observe in the data the physical events that have taken place in that stop. So we can't do the second one, which you suggest, which I agree would very much simplify our life, or in the sense it would lead to better estimates. But we do the first one, which is we also model the probability of an arrest subsequent to the events which have just taken place, which indeed I'm showing you the models for right now.
Okay, yeah, because I was just wondering, because at in Albany, in upstate New York, with the New York State Division of Criminal Justice Services, so at one point with their data, so they have the criminal records for everybody in the state of New York. So if somehow we're able to merge that data with the New York State, I mean, the New York City database is different compared to the rest of New York, but somehow if you think of a bigger project where you're able to get hands on that data, then you would know the complete history of these people.
That's true, but you need to have identifiers of the individuals in the stop and search data, which at the moment are not provided. I don't know. It's certainly something which will look into. I'm just wondering. Yeah, I mean, it's a shame they don't provide any information in the data set about what information got exchanged, whether something new was discovered. What we see are only things like weapons discovery or drug discovery, not whether there's a prior arrest record or whether, yeah, something to that effect.
Got it. Okay. Thanks.
Okay. So now the next and trickier part is to say, well, suspected crimes are told to us in this police data set, and we're taking them at face value. What if they are not so accurate? Or the more general problem, if data about the variable giving rise to statistical discrimination, namely beliefs, is itself not available. And we can think of many situations in which there is discrimination. We believe we know the source in terms of statistical discrimination, but we don't observe the variable which we think is the source, such as credit histories in bank lending, or efficiency, leadership abilities, work ethic when it comes to a job situation involving recruitment or promotion. So the key idea which we're saying is, well, let's propose a distribution for beliefs conditional on the treatment, on the outcome, and on other relevant covariates. So in our working example, this relevant covariate is going to be precinct, because clearly the police could say, depending on the precinct where we are, our beliefs are tuned in a certain way. Propose this distribution, take Monte Carlo draws from this distribution, and therefore simulate a beliefs variable. The mechanics behind this come from this 1983 paper by Rosenbaum and Rubin, who are using this approach for investigating a confounder sort of situation. So sensitivity of treatment effect to some binary unobservable. And then there's a very clean implementation of this idea in this paper by Ishino et al. This is again it's a paper trying to estimate the effects of a job training program using propensity score matching and saying, what if there's a confounder? Let's simulate it. So we're using that machinery, and I'll say exactly what we do in a moment. the sort of huge benefit from our perspective of employing all of this stuff and all this structure is that we can now answer a question like, how adverse must beliefs be in order for statistical discrimination to account for observed race-wise differences? Which goes back to some of the questions you posed at the start, which is, well, this adversity of beliefs may or may not come from experience, may come from hearsay, may come from my colleague, may come from prejudice. So I don't know exactly what the ingredients of it are, but I can now compare the distribution of these beliefs with known empirical facts from history, like weapons discovery, like drug discovery. And I can make up my mind about saying, how far are those beliefs from what is empirically observed? Indeed, can I now impose a model of, as you said, I think Shrovik, you said maybe some time back, that 7 in 10 of what my colleague told me about resulted in drug discovery. And if I impose that model, well, how far are my beliefs from that model? And do they go on then to explain statistical discrimination of a magnitude which makes sense given the observed race-wise differences? So that's sort of the overall benefit of using this kind of simulation-based approach.
So Sunil, this is similar to a Bayesian idea, right? So basically you're estimating the.
Very much, yeah. We're specifying a prior, we're seeing how the results change, and then we're specifying a range of priors and seeing how the results change. Exactly. So we're going to assume officers' beliefs are grounded in the sense of empirically defined by historical experience, shaped by past experience. And we're going to, in this talk, I'm focusing on weapon or contraband discovery. In the paper, we look at these separately as well. And we're going to specify beliefs as a binary variable B, which can be 1 if we think the civilian is carrying a weapon or contraband, suspicion. Use data on past precinct-wise hit rates. By hit rate, we mean the proportion of civilians who were then discovered after a search or frisk to be carrying weapon or contraband. We use historical data from the 2017 and 2018 part to then specify simulated beliefs for 2019 data. And we're going to now estimate discrimination only for 2019 using these simulated beliefs. So here is the distribution of precinct average hit rates for these 3 things. I guess at the moment, it's probably best if we only pay attention to this one, but it's not, the same story carries through. The only point of this picture is to say, look, there is substantial variation across precincts in these hit rates. So this is from 2017 and 18. Therefore, it makes sense when you're going to simulate beliefs to take precinct into account. And so this is what we're doing. We're simulating these beliefs according to historic precinct-wise hit rates for whites and for blacks and Hispanics. So we're simply saying, if this was the average for whites, for blacks, for Hispanics in a given precinct, let us simulate a beliefs variable according to that average. But to make it more interesting, let's also multiply the observed hit rate by some number m when it comes to blacks and Hispanics. Why would we do that? Because then we can bring this question of adverse beliefs into the picture by saying, how high does m have to be? And as m rises, how does statistical discrimination rise? How high does m have to be in order to explain the observed difference in search and frisk as statistical discrimination?
Just a quick question. So I'm just wondering that could you rather use, so for example, like a blinder Rohaka kind of decomposition. So for example, you have the observed characteristics for blacks, whites, and Hispanics, right? Mm-hmm. So can you, keeping all the other characteristics the same, can you switch from, so instead of a black person, if a black is 1, say Hispanic 2, and white is the reference is 0. So can you try to look at if a black person in fact was not black, but a white person with the same other observed characteristics, what would be the estimated effect? And then look at these differences. So essentially keeping all other observed characteristics the same, you just change the or switch the race indicator and
So,
estimate defense on certain.
so I think the answer to that is yes, provided we make some very strong assumptions. And the strong assumption looking at this picture would be that none of these M variables or the Z variables are actually mediators. Okay, why? Well, if they are mediators, which means they are affected by A and they go on to affect Y, then they are intermediate outcomes. If they are intermediate outcomes, then we know from the causal inference literature, you should not be controlling for intermediate outcomes. You should not condition on them. Because for the simple reason that when you talk about manipulating the race, actually you need to talk about manipulating some of those intermediate outcomes. Now, you said if we hold those fixed, we would be isolating taste discrimination, which in a way is true. But if you do that, you're sort of jettisoning or sort of ignoring the whole machinery and definition of statistical discrimination, because statistical discrimination is arising from one of those things which we are now holding fixed. That's point one. Point two is when you do a blinder Oaxaca kind of setup, what you're doing is you're not holding you're holding the mediators fixed in the sense you're holding the distribution of mediators fixed for the full sample. What you want to do instead is hold the mediators fixed at, let's say, the reference distribution for whites, and then switch the treatment from white to black, or hold the mediator fixed at the distribution for black and switch the treatment from black to white. Instead, what you're doing is you're holding the mediator fixed at the pooled distribution for black and white, and then switching the race from white to black, which is going to give you some causal estimate, but it's not really the one which you're after if the definition you're after is taste discrimination.
Yeah, okay, agree, yeah.
So that's my sort of criticism of the blinder Oaxaca, but in general, regression-based approach in more generally.
Okay.
Okay, so we do this, and here are our results. So I just like to talk through the different parts in the picture, for which I need to get the annotation back up.
Sunil, just before you do that, can you just go back?
Sorry, go back where?
Go to your previous slide.
Yeah, I will if I can get the keyboard to move there. Okay, yeah.
Okay. So you've chosen precinct wise, right, as the prior, right?
Correct.
And
Yes.
and from your table, it looked like it was both precinct and date and time that was leading to this.
Very, very much. Yes, yes.
So
Agreed.
wrong place, wrong time, basically.
Yeah.
So why did you pick precinct and not date and time? Is it just
So-
easier to do?
Well, one is that it's easier to do. But second is if you look at these values and you look at how the statistical discrimination estimate changes as you add more and more of these variables, similarly taste, see that the drop when you add precinct is substantial.
Got
The
it.
additional drop when you add date and time is very minor. So
Right.
yes, I agree with you. A better job would be not only date and time, but also physical characteristics. And you have sort of thousands of these cells of
Yeah,
different
yeah, yeah.
combinations. And in each of those cells, so the empirical problem is many of those cells will not have observed outcomes inside them, or they'll all be
Yeah.
0 or all be 1. So that's the empirical problem. But in terms of relevance, I think the point being precinct explains a lot of the lion's share of the variation. So that's why
Right.
we stick to precinct.
Got it. Got it.
Okay, so here is this picture, and I'm going to heroically try to annotate as well. Right, so baseline odds, as you remember from the table of results, is roughly 1.68. And it's going to be a bit different here because this is now 2019, but the number is quite similar. Beliefs equal to past hit rates. What does that mean? That means that if I don't change the empirical average of hit rates for blacks and whites, if I simulate from what was already observed in 2017 and 18, in other words, this number M on the previous slide equals 1, then I get beliefs which coincide with past hit rates for everybody, white, black, and Hispanic, at which point you can see that my estimates of discrimination are very similar to what I already saw in my using the full data, 2017, 18, 19. In other words, Statistical discrimination is basically nil because the odds remain 1. Taste discrimination is some number around 20%. So this is a lot lower. Both these numbers are a lot lower than the observed baseline odds. So now you can say, well, if we want to explain the observed difference in outcomes in terms of statistical discrimination, how adverse must the beliefs be? So now we start boosting the hit rates for blacks and whites artificially by multiplying the observed number with M. And so M equal to 2, M equal to 3, and so on. So roughly at M equal to 3 point something, 3.2 or 3.3, it's then that statistical discrimination estimate is very high, and it is of comparable magnitude to the baseline odds. Now, of course, these are bounds, and the idea here really is to say, well, can we do a bounds-based exercise to see, yes, we know precinct is going to explain a lot, but let's do a thought experiment. If the difference is fully explained by suspicions, how bad or how adverse must those suspicions be in order for observed differences to map onto statistical discrimination? And that's the answer which we're providing here. Now, we've used a very simple model for extrapolating beliefs, which is hit rates, which is therefore based on average. You could specify other models like median, or like a more selective experience of, let's say, the past 1 month or past 2 months as different from pooling 2 years of data, which we've done. And so that's why I was saying you can use a whole myriad world of models, specify beliefs, see what the estimated discrimination is, and then again get a sense from that of what are the bounds on this problem. So I'm going to stop here and happy to answer more questions.
Okay, so we have about 10-15 minutes for questions. I just wanted to ask one, do you have any information on the police officers themselves?
No. There are some papers where they observe the race of the police officer themselves, and they use that as a way of identifying taste by looking at the matching of race of the stop person and the officer, but NYPD data does not give you that.
I see. Okay. All right. So anyone else have anything to ask?
Yeah, I have actually, I'm going to pick on Sunil's clarificatory point on Oaxaca, because of course the starting point of all these things is usually an Oaxaca decomposition. So it'll just help. I think it'll help all of us also exactly understand. I think so. You have a black and white, covariates, various covariates, and they have a different distribution. And the idea of the Oaxaca is to basically take one as reference. That means assume that both have the same distribution, whichever be the one, and then essentially that explains some part of the outcome. And then the idea is, I guess, the residual part of the outcome is going to be something which is more taste, right?
Very much, yeah.
So you said that you didn't like that, and this is I didn't get that exactly. So what is it that where this is slightly different, or rather a lot different?
So, I mean, my understanding of, and please correct me if I'm saying it wrong, my understanding very much is to say, let's try to see difference in outcome, map it onto two things: difference in the distribution of interesting covariates and difference in the distribution of the key covariate, race, the treatment.
Right.
That doesn't cleanly map onto the counterfactual exercise we are undertaking, where we are saying we want to hold the distribution of those key covariates, the interesting ones, the confounders, not fixed, but a special kind of fixed, namely the distribution for the whites or the distribution for the blacks.
Okay.
And then vary the treatment alone. So that's different from saying we're going to hold the distribution fixed at the pooled distribution for everybody who is in there in the sample. And correct me if I'm wrong, but that's my understanding of what this method is doing. And therefore, that is the clear distinction between that and the sort of the definition of, if we go back to the definition over here in terms of this one, in terms of the difference in these expectation terms, which is very clearly saying we want to hold the Z and the M distribution at what it attains when treatment is held at reference level A, and not the pooled average.
Okay. Yeah, I guess also the case that the relationship between the M's and the Y's are also held, I mean, the Oaxaca at a reference level, right? I mean, the betas,
Yes.
right? So it's
Yeah.
you're saying no. So it's the pool distribution, but
Yeah.
the mapping between the M and Y is where the referencing goes in Oaxaca. Whereas in your method, basically the distributions of the covariates are where you're holding those distributions, at reference level.
That's right. Yes. And in that, so this method, I guess, could generalize. You could say, well, why don't I permit for a different beta? Why don't I have an interaction term between A and M in the model for Y? And you could do that if you think that a different beta is justified. I guess, yeah, the other thing I'm just thinking aloud here is that the same logic applies why the blinder Oaxaca then won't map on very cleanly to the kind of RCT that the Mullainathan paper does. Because again, there, what is the aim? We give these randomized names, but we're trying to make sure the distribution of the other covariates, education and so on, is held fixed. And held fixed, again, is different from saying pooled at the average. Instead, we want to hold it fixed at the level of certain individuals or at some profile which we as experimenters propose.
I see. Okay. Yeah, I think I understand. Yeah. Thanks.
Final clarification point is all of that both those words collapse into one if the model through which you're estimating Y is a very simple OLS. So A, linear, and B, no interaction terms. If it's that, then these two words coincide. It's only when the model is more complicated or there are interaction terms involved that then the point I'm making has a sort of substantial implication. Otherwise, they are one and the same. If it's a very simple model with linear A and B, no interaction terms, then they coincide.
Okay, thanks.
Sunil, one more thing so you said that this M reaches some point around 3.
Yes.
Can you just explain, like, what does that mean? I don't think I understand it.
So let me go to one more slide here, which I'm going to say what exactly we're doing when we're extrapolating hit rates. So if we look at the last paragraph, we're saying, look, let's look at the empirical average, the proportion of civilians of certain race in certain precinct with some outcome who have been discovered to be holding weapon or contraband. So that's how the hit rate comes about. Now note that this is observable only for those who actually were searched. So the people who are not searched, maybe they are carrying something, maybe they aren't, we don't know. So to extrapolate to them, we need to put in some more multiple. And that's what we're doing here. We're saying, okay, let's come up with some multiple K to extrapolate to those who are not searched so that we can specify a hit rate for everybody together. Now note what K is going to do is K is really, really small. In other words, we say people not searched or not carrying. In other words, the police are highly efficient in targeting the searches. That's K equal to 0. And likewise, K could be a bigger number, and the bigger K gets, the worse is the targeting. So that's another sensitivity parameter behind the scenes, and we are keeping it just at 0.5. In the paper, we tried 2 other values. But with that in mind, now we have got a hit rate for 2017-18, which is some proportion, let's say it's 0.2. Now, 0.2 for whites, let's say 0.3 for blacks, 0.3 for Hispanics. Now we're saying let's take draws from a uniform distribution to be able to simulate the variable B. So 0.2 for blacks, 0.2 will be the average of B for blacks, 0.2 will be the average of B for whites, 0.3 for blacks, 0.3 for Hispanics. That's one part. Second part is to say, well, actually, let's try to make the observed numbers worse for blacks. So instead of 0.3, which is the empirical observed number, let's multiply it with something. Let's make it bigger. Let's make it 0.6, 0.9, or the upper limit would be 1. So as we multiply it higher and higher, we're saying the beliefs about blacks are actually more adverse than historical hit rates would suggest.
Right.
And that is what we're trying to do here on the x-axis in this picture.
Okay.
So
So it seems to be, so if it's 0.3, then 3 times 0.3 is what, 0.9, right?
yeah, so you can't really go higher. So actually
Yeah.
the observed hit rates are pretty small. If you look at these precinct averages, there are some where they are large, so they get bounded by 1 quite fast. But the median numbers are something like 12 to 15%. So
Yeah.
you could multiply that quite a bit and make
Yep.
those beliefs more and more adverse.
Right. Right. But that would also suggest that your M has some logical upper bound.
Oh yes, so your M has a logical upper bound for depending as a function of the precinct hit rate.
Yep.
Yeah.
Okay. All right. All right. Any more questions, clarifications?
Yeah, I had one clarification, which is that when you are jacking up the M to increase the statistical discrimination, why must the test discrimination estimates fall?
So, I mean, if you look at this picture over here, basically when you're jacking up the M, you are strengthening the correlation between race and suspected crime, and you're increasing the variation, therefore, in suspected crime corresponding to variation in race. So you're artificially imposing on the model that there is less and less residual variation. And taste discrimination is picking up that residual variation. So that's why it has to fall if something else in the model is artificially being made to vary more and more strongly in tandem with the treatment.
I see. But you know, where I'm sort of struggling is initially when you are jacking up M, you are still quite below. Well, what would be the sum of what would be the sum of taste and statistical discrimination odds be? Like, my question is, you want to make the statistical discrimination equals to the observed one. But what is the sum of the two?
So that actually is not a trivial question at all. That's a highly technical question, and there's a big literature on saying how can we basically break up the total causal effect, which is the variation in Y corresponding to variation in A, as natural direct effect and various little indirect effects taking place across the spectrum of intermediate these mediators, basically.
Right.
And my short answer is there is no clean decomposition unless you have a very simple model in which there are no interaction terms.
Okay.
But otherwise, there is no clean distribution of that. Under certain modeling assumptions, you can specify a breakup, but we are not doing that in this paper, not least because it's very hard to extrapolate from the single mediator case of just one Z to the multiple mediator case. And even worse, if there are causal relationships within the mediators, namely
Right.
like if M1 affects Z or if M2 affects M3 affects Z, something like this, then breaking that up becomes even tougher.
Because I was wondering, what we see in the observed data is a sum of the two, and you are, by jacking up the M, you are trying to see when would only a component of the discrimination, mainly the statistical part, would be equal to the observed. But when statistical discrimination is so high, your model is saying taste-based discrimination is on the other direction.
It's
And
negative.
so the sum of the two would could be less than the observed, right? So what we should care about is matching the observed with the sum of the two and not with the statistical. So I guess the another way of putting it is that you could alternatively ask what value of M would make the sum of the two discrimination equal to observed and not statistical being equal to observed.
So I take your point. It's something we are working on, but it's not going to be for this paper, for the reason of how technically complex it is to be able to give this decomposition of the causal effects. But I take your point. I guess I would just argue to you that in the discourse, at least on stop and search, the discourse very much is suspicions are justified, they drive the outcome. So equating statistical discrimination with observed differences is an important question in its own right. But I agree with you from an intellectual point of view. I would very much like to write the paper where I can add those two and therefore provide the decomposition of the total causal effect, or the total causal effect of race into these two, and if there are other bits as well, because depending on a multiple mediator setup, there will be other bits as well.
Right.
So, yeah, so I take your point.
Yeah, but Sunil, if Sabya's points were true, then it would mean that in the first round, when you're estimating stuff, then you still have things on the table, which means that you don't have the optimal values, right? I mean, the fact is that, I mean, I'm just thinking about, so you try to fit the data patterns using some sort of a model, right? And if you could keep the taste discrimination the same and jack up something else in the model and make the model predictive, that means that your initial prediction was not optimal to begin with. So you can always do trade-offs between your, between various things in your system, so that, you can ask, okay, if one goes down, how much the other one has to go up by to be able to get us, whatever we had got to begin with. That's a valid question. But if you could keep one of them the same, I mean, I'm thinking in terms of parameters, but I guess there'll be some mapping in terms of what you're doing, and change the other thing. And now I'm getting even better predictions. That means your initial prediction was not good enough, was not optimal.
But for that to happen,
sort of idea like that, right?
Okay, but the thing which is empirically given to you is the variation in the outcome corresponding to variation in the treatment. Those two things are fixed in the data. All we are playing really with are the things in the middle happening. What else varies, co-varies with race or co-varies with treatment in a way that explains different arms or different causal mechanisms. So I don't see how you could hold one of those variations fixed, boost the other variation. When you boost the other variation, hold one of them fixed, the variation in y will have to increase.
Yeah.
So so that's sort of the logical constraint on undertaking that exercise.
All right. So we are mostly out of time. So thanks. I want to thank the speaker for a really nice talk. It was very interesting, and all the participants as well for your questions. So I'm going to formally close the seminar now, and we can